In the area of computer graphics and animation, one of the most important concepts is a special case of implicit functions, that one that gives a circle. If I give a constant 10 and I say that I want to make it equal to the relationship of the square root of x squared and y squared, the result is this circle. The lines in here represent the areas where the combination of the parameters x and y give us a result, the constant 10. Keep in mind that in this type of systems, the variable x is independent from the variable y. But if we look a little closer to the relationship between x and y, we can find some interesting attributes. Let's take a look at this circle. Let's suppose that we have a dot that is traveling around the circumference of this circle. At any given point in time, if we put the circle center in the coordinates 0 in x and 0 in y in a Cartesian plane, and we assume that the radius of this circle is always 1, we can project a line that starts from the center and touches the center of the dot, therefore creating an angle relative to the horizontal line in the x-axis. If we know the value of this angle, we can calculate the value of the position in x and the position in y where that dot is in the Cartesian plane. To do this, we will use the concept of the sine and the cosine functions. The position here represents the elevation in the vertical axis, which is y. Using the mathematical formula sine of the angle theta, which is going to be this angle right here, we get the position in the y-axis of this dot in a circle that is centered and has a radius 1. You can see here that as the dot moves around the circle, the elevation or value in y increases or decreases depending on the particular position where it is around the circumference. Sometimes the values will even get negative, as the value of the sine is defined between -1 and +1. So the elevation is defined in a range of values that goes between those two numbers. A sine wave that looks like this summarizes the changes in the vertical axis of the position of the dot. This animation summarizes the same process in a way that may be a bit easier to see. You can see that as the position in the vertical axis increases or decreases, so does the elevation in the sinusoidal wave. A similar concept is that of the cosine. The cosine will represent the same type of relationship, but for the x-axis. Let's implement this using Python and pygame. Let's start by dividing our program in 3 different sections, defined as the modules or libraries, the definition of data that contains information that we're going to use to create our algorithm, and finally the coding process. In the module section, we're going to use pygame, and we're going to use the math library that contains the method to calculate the sine and the cosine functions. In the data definition, we'll need to specify some parameters that will allow us to handle the screen using pygame. The most important one is a hyperparameter called the screen, a tuple that contains 2 integers, the number of pixels per width and the total number of pixels per height. Then we're going to need to create a variable called display, which uses the display sublibrary of the pygame library and the setMode method. This will allow us to build an actual screen. Now that we have these 2 elements, we need to decide how we're going to draw the circle. Let's create a data definition for our circle. This circle will be an instance of the class with the same name, and it represents a circle rendered in the middle of the screen. And let's put it like this. The class circle will contain as its constructor the instance of the class that is called self, and let's also add a radius. Self.r will be equal to r. The position in x will be equal to the width of the screen divided by 2, because we want it to be in the middle of the screen horizontally, and we want it to be in the middle of the screen vertically as well. So we're going to call this y at a screen at index 1 divided by 2. Notice the use of double forward slash, and for those of you that are not that familiar, this means integer division. It's going to give us a number as a round number. Then let's specify the color. Let's make this a white circle. And now we can start drawing it. So we're going to create a helper function named draw that is going to take self. Any method inside of the class has to pass self. And we are going to draw a circle using the draw sub library and the circle method. We're going to render it in the surface known as display. The color will be the color that we assign to that circle, and the center will be at the coordinates self.x, self.y. Let's make this of radius self.r and the thickness of a line, so we don't want the circle to get filled, but rather being hollowed. It's going to be of thickness 3. Those are all of the attributes that we need to render a circle. It's pretty easy. Now let's create a circle here. Let's call it circle 0, and it is going to be an instance of the class with the same name. Let's make the radius something around 400 or 350. The diameter will be twice, which is 700, which is closer to the dimensions of the screen while keeping some padding. Let's see if we can render this. In the coding section, let's call the draw function and the update function. Let's define them here. And these are two functions that we will always need to use whenever working with pygame. Let's run something forever. This is going to include the drawing process and the updating process. If I run my window right now, I would find that the window is not interactive. That means that I can't click and drag, or if I click, the program will halt and it will break. So I need to make sure that the program understands that I want to interact with that window. To do that, we use a for loop that iterates or loops over every single event in the list of events that pygame has, which we can access using the get method. If the name of the event is of type quit, which is a constant in pygame, then we can use the quit method, but this time with lower cases. Let's go to the draw function. The draw function drawing implies three things. First, changing the color of the background, which is our display or surface. And we're going to pick this color, which is the same color as the background in VS Code right now. Then we're going to render whatever we want to do, something that is special to our algorithm. And in this case is our circle 0. So we're just going to call draw. And once we're done, we make sure that we send a handshake to the programming language that is actually rendering the screen by using the flip method. Let's run this program and let's see what we get. There it is. We got our circle. Now this circle is centered. The position X and Y will represent the center of an invisible Cartesian plane. Let's draw a dot. That will be a property of the circle. So let's add a couple of attributes here. The first thing will be the dimensions of the dot. The dimensions, let's say, is going to be of 10, radius 10. We can modify it later if we decide to do so. Then we need to define where in the X and the Y axis this dot will live at any particular time. Those values will be calculated based on the angle. So let's define an initial position for this dot around the circumference of that circle. Then let's place the X, which is a change in the value in X. That sometimes is referred to as the velocity. In this case, it's just change in X. And that's going to be equal to 0 at the beginning. And we do the same with Y. In the draw function, we are going to draw not only the circle, but on top of it, we're also going to draw the dot. So to draw the dot, we need to calculate the position in a Cartesian plane to where that dot lives. Let's create a helper function to do that. Let's call it get dot position. This is going to receive self like any other method in the class. And what we need to do is to define self.dx the cosine of the angle. This one is going to give us a value that goes between -1 and +1. So we multiply by the radius to place it overlapping the circumference of the bigger circle, whose radius is self.r. We do the same, but for the y-axis. And this time we will use the sine rather than the cosine, while still multiplying it by self.r. Before we leave, let's update the value of the angle. And for now, let's just leave it at 0. We're going to get back to this one in just 1 second. Let's go back to our draw function. Let's copy this line and paste it below. The dot is just another circle that is going to be in the same surface. And the color, let's change it to red. The position of that dot will be given by the initial center of the circle plus the change in the x direction, and the position y that represents the center of the circle plus the change in the y direction. The radius of this circle is no longer r, but rather self.dot size. And this is going to be a solid dot. Let's run this and let's see what we get. Okay, so we have a dot that is in the center of the circle. And the reason why it's not touching the line of the main circle is because we haven't called the function getDotPosition. There is multiple ways to do this. I'm just going to call it in the draw function itself. I'm going to call getDotPosition. And I'm going to run the program once more. Once we run it, you can see that the dot is now overlapping the main white circle. Let's go back to line 32. Here, you can see that we are technically updating the value of the angle, but the magnitude of that change is 0. Let's change it to 0, 0, 1. And let's run the program once more. Notice how the dot is gonna start updating its position around the circle, sort of making the trajectory of an electron around the atom. Before we finish this tutorial, let's create a quick animation that will demonstrate some of the interesting applications that can be applied using polar coordinates. I'm gonna start by drawing the field only once per animation. I'm going to accomplish this task by creating a new data definition, which is going to be a predicate, which is going to be a boolean that asks if this is the first frame. So I'm just going to call it first. And the boolean is first will start as true in the very first frame, whether or not this is the first frame. Is first starts as true. In the draw function, I'm going to create a global reference to the isFirst variable. And down here, I'm going to use an if statement. If this is the first frame, we change the color of the background and then we turn that flag or switch off. This if statement will never be run again. The reason why I'm doing this is to demonstrate the interesting effect that accumulating frames has when working with these dots. The effect is that of coloring. So what happens if in the update function we also modify the dimensions of our circle? Let's change the value of the circle 0.r and let's make it a little smaller, something like this. And once it gets too small, maybe let's apply the modulo, or maybe let's use an if statement. If the circle 0.r is less or equal than 0, then the change that we will apply will be positive. So let's create a new variable, direction, inside of our circle. So let's put it in here, self.direction equals 1. The value will represent whether we are going bigger or smaller in the circumference of our circle. And let's use it here. So if the value is less or equal than 0, circle 0 dot direction equals positive. We want to start growing. Otherwise, if the circle 0 instead is bigger or equal than the initial radius, which was 350, then we set the direction backwards by making it -1. And once those changes have been applied, we just change the radius of the circle. And instead of using minus equal, we can say plus equal 0.001 times the circle 0 direction. Okay, let's make it 0.01 and let's see what happens. Okay, so that gives an interesting effect, a form of procedural art, where we generate a spiral. Once the circle reaches 0, then it will start expanding. And here it comes back. Nice. So this is a really nice application that hopefully serves as an introduction to the concept of polar coordinates.